I think I left off last time. We're talking about physical methods for microbial control, and I'd gotten through several things relating to temperature, both use of heat and cold, and related to that is desiccation. But there's more in the way of physical control methods, so we'll talk about those now. And so currently we have several forms of electromagnetic radiation that can be used for controlling microbes. We call it electromagnetic radiation, EMR. And all of these are based on movement of theoretical particles through space they're called photons. So this little dot right here is a photon. Is a photon, let's say. And then as that moves through space, it's going to move in a wave form. So each photon has its own sort of waveform. And the thing that differs from one class of these to the next is the distance between the peaks in that waveform. Right? I know that's a bad picture, but from peak to peak, that's a wavelength. And these are measured in pretty small units of measurement. Most appropriate unit of measurement for measuring wavelengths is the nanometer. That's a billionth of a meter. And you can see up here, this little graph shows the ranges of wavelengths of different forms of electromagnetic radiation. The main thing to remember is the energy content of a particular photon is negatively related. It's inversely related to its wavelength. So the shorter the wavelength, the more powerful it is. And so radio waves, you can see, occupy this range here from about 1 million on up to 100 million nanometers. Now, a nanometer is a billionth of a meter. So these are, not quite a full meter in length. That'd be about a yardstick long, 36 inches. So they're approaching that length, but not quite that long. So radio waves are very low energy waves, thank goodness, because they're just traveling through the air, through the space around us all the time, and could be quite destructive, as abundant as they are. And then we have infrared radiation, which is the radiation given off from very, very hot objects. Like you had a poker and you stuck it into the fire and it got it red hot. It'd be emitting infrared radiation, which is, in large enough amounts, enough to, say, cook a turkey or something like that. But anyway, it's not as energetic as some other types of radiation. Visible light, the light that activates the photoreceptors on our retinas, is even more high energy than infrared radiation. And when it's applied intensely enough, it can start fires and that sort of thing. You can see that its wavelength is even shorter than that of infrared. But down in this range here, below where we can see, we've got several forms of radiation. Ultraviolet, which is sometimes called UV, and you can see the last sort of band in the spectrum of light that we can actually see is violet light. So this is a little bit beyond that, hence it's called ultraviolet. And you can see it occupies that range and wavelength somewhere between, say, 390 nanometers on down to shorter wavelengths approaching, say, 100 nanometers. So in there. That's ultraviolet. And then even more energetic forms of radiation have very short wavelengths, and those would be gamma and X-rays. So the first one that's considered here would be the gamma rays, the X-rays, and also what we call cathode rays, which are utilized in forming images that you can see with the television set and that sort of thing. I don't know much about their generation and how they're used, but those are an example of a type of powerful radiation called ionizing radiation. So ions are atoms or parts of molecules that have been acted on to the point where they've lost some electrons or gained some electrons, and that has altered their charge. And so this is radiation that can cause ionization. It can cause gain or loss of electrons in molecules that are exposed to it. And one of the molecules, of course, that living things need to be able to function is DNA. And so this down here is a picture of a DNA double helix. And you can see this radiation source, which could be something like, I don't know, radioactive substance such as uranium-235 or some type of plutonium or something like that. It's emitting these photons, and this stuff is powerful enough that it actually can go through a barrier like, say, a piece of cellophane or plastic. And it can go all the way through that and enter cells, pass through the outer covering of the cell, and make its way all the way into the nucleus, or the nucleoid, as the case may be, and literally fracture the DNA. So here's a break. So that's DNA strand breakage is what we call that. And that is destructive. That is going to really limit the viability of that cell or the organism that contains that cell if it's a multicellular organism. So yeah, this literally breaks DNA, and those exposed ends of the double helix are, ionized as a result. That's going to shut down genes and is going to kill microbes especially. So we've figured out ways to harness this and use it for sterilization. This is radiation that can act as a sterilant. Now, the good news about this is if you take, say, medical supplies or bacteriological media or food products and you expose them to these photons of ionizing radiation, say gamma rays, the material that's been impinged by that does not retain the radioactivity. In other words, it's only been, in the presence of it, but it doesn't hold on to that radioactivity, if you know what I'm saying. So you irradiate some foods like these red raspberries here, which are in a plastic container. You can see the container. There's actually a barrier over that, some plastic, that prevents the entry of contaminants and microbes and things. And you can see this little symbol here is an international symbol for use of something that is, environmentally friendly, not something that's going to reside in the environment after it's been applied. So that's a symbol that indicates this food has been treated with ionizing radiation. Now, it destroys bacterial and other microbial cells, but it leaves the food intact. And the food is perfectly fine in terms of flavor and color and texture, as you can see. So that's a win-win. That's a win for the consumer because now they can purchase that, but it's also the win for the farmer because he or she's going to get a profit from having sold those. Even after 5 days or more on the shelf, these are looking good. Now, if you don't irradiate and you don't have a setup where you can keep things really fresh, and you were to say have some harvested berries and you put them in a container and stuck them on a shelf without adequate refrigeration or something like that, this is what happens to them. They basically fall victim to these fungal organisms, these molds, and you can see they're pretty much being liquefied here. So you're not going to want to buy those unless you were desperate and had to have something to eat. You're not going to pay full money for those. And the farmer is not going to get a profit from those. They're going to get thrown away more than likely or composted or something. So yeah, this is potentially an important thing, especially in a world with a lot of people and there's, food insecurity and that sort of thing. Maybe this is a good way to go, right? But I'll just tell you this, those berries over here are not radioactive, trust me. They're just not. The photons have struck, they've killed the microbes, they've moved on, and now that's ready to be eaten. So then we have, if we've got ionizing radiation, it stands to reason that we're going to have non-ionizing. And this is your UV. Okay, so this is UV radiation. Nowhere near as impactful as gamma rays and X-rays, but it still is effective as a sterilant. It can sterilize different things, like water. If you want to treat water, if you want to treat air in a laboratory, if you've got air that's making its way into a room or some other space, if you have ultraviolet lights applied to that stream of air that's circulating, you can maybe kill some of the organisms that are present in that. And we're finding now about droplets and aerosols and things that can bear viruses and so on, but they're actually pretty dangerous, even though we can't really see this. So UV radiation can be helpful. We can use it as a sterilant in a laboratory setting to sterilize lab equipment. There are UV sterilizers that can be used for delicate lab equipment. You don't have an autoclave, or if you've got something that's not autoclavable, UV radiation can be used. So it's not quite as potent as gamma or X-rays, safer to use. As you see here, one indication that it's not as potent is the fact that in this scenario here, this hypothetical scenario, there's no barrier between the source of radiation and the cell that's being irradiated. So if you did have a barrier, as is the case down here, like glass or plastic or something, UV is not going to get through. So that points up the fact that it's not as powerful, but it's powerful enough to do this. So this is a hypothetical piece of DNA here, a double-stranded molecule that's got A's, C's, T's, and G's on one side, and then you got on the other side complementary base pairs, A's, C's, T's, and G's as well. Now, anytime you have, and these are obviously thousands of base pairs long, thousands and thousands of base pairs long, but anytime you have a situation like this where you've got a pair of A's bound to a pair of T's below, these are hydrogen bonds in here, by the way. Those are H bonds. Anytime you have that and you expose pieces of DNA with those to ultraviolet radiation, just sort of a quirky thing about these particular bonds, those H bonds will break. And you'll wind up with unbound adenine and thymine right there. So notice in here, there's no bond. But to replace that, we wind up with very tight, very strong covalent bonds right here. These are covalent, which, as you know, hopefully, are very, very strong. H bonds are weak, but these are strong. And what happens is, say, for example, there's an enzyme, a polymerase enzyme, we'll just call it a POL enzyme, and it's moving along and it's reading off this DNA for the purpose of copying it. When it hits this right in here, when it hits that, it's going to come up against a roadblock. It's like, whoa, Nelly, we can't go past that point. That's like a set of railroad tracks where one of the pieces of track is missing. And so the DNA polymerase can't go anywhere beyond that. So it can't be replicated. It can't be transcribed. So it's going to shut down activity in the cell, just by virtue of a more subtle kind of thing, as opposed to what happens with ionizing radiation, where it literally breaks the DNA. Here, we just have a chemical change between thymine residues. So this is simply called dimerization. All right, that's dimerization. That should be an A right there, sorry. And so that's one thing that ultraviolet radiation will do, and that's how it's effective. It doesn't really break the DNA, but it reconfigures it. So you can utilize that. Another means of physical control, it falls into that category, but it's it doesn't. It's got a pigeonhole of its own. It's not like radiation. It's not like temperature-based control agents. This is simply using a filter. So it could be like a piece of ceramic that's not glazed, so it's got pores that are open, or it could be there's what we call Cefidex, and we've got nitrocellulose, and we've got even paper filters. And if you place a liquid bearing particulates in it that you would like to remove from that liquid, you can pull it through the filter or allow it to just simply pass through it by way of gravity. And then as it goes through these little interstices, these little breaks in the filter, it winds up over here. And that's our filtered liquid. So that's called a filtrate, by the way. You got a filtrate there, and it's pretty clean. It's devoid of a lot of things. And if the pore size is small enough, you can even eliminate viruses and probably prions. And so you can, if you have a filter that is, made with pores that are very, very tiny, you can exclude all microbes and wind up with a sterile filtrate. So that is possible. This can be sterilizing. So yeah, this shows the setup that's often used in laboratories. You can set up a vacuum that is attached to this side neck flask here. That's called a side neck flask or a filter flask. And you've got your filter sitting above that. And so a vacuum is generated inside of the filter flask, and that fluid will go down through the filter and will accumulate there as filtrate. Set up apparatuses like that will speed this up and make it go a lot faster. You can do it with liquids. You can do it with air in some high-end situations in labs and hospitals where there's great concern about dangerous microbes that could cause disease. You might filter the air. So like a lab that's using something that's like a biosafety level 3 or 4 type of organism, they might have air filters that are sterilizing and use ultraviolet radiation and other means to limit the entry of microbes into and out of their labs. So that's filtration. Okay, so that does it for physical means of control. That's by no means the end of the story on that, but those are the high points. And so now we can talk about chemical agents. And so think about all of the different terms that we used earlier in referring to different levels and different kinds of microbial control, like disinfection, antisepsis, sterilization, and so forth. Basically, these chemical agents can do all of those things. We can find an agent to do virtually anything we want to do. So in these chemicals, when we apply them, some of the desirable things about them you can review. But yeah, you don't have to have a whole lot of some of these. Some of them work in very small concentrations, which is good news because if you've got, say, a gallon or two of it, you can kind of extend it for a long period of time using small amounts as you go. Some of these things can be extended further by solubilizing them in water, so making a solution with them. Or you can do that with alcohol. If you've got a substance that is more soluble in alcohol, then you can do that. And that's going to give you even greater capacity to extend this and to use it to disinfect or de-germ large areas. Generally, they're pretty stable. If they're not that stable, you can do things like contain them in a light restrictive container, something that's opaque or brown. That'll make many of these more stable. Um, but yeah, generally that's the case. They're pretty stable, which means they don't break down and weaken over time. Most of them are broad spectrum, which is good because if you don't know exactly what the microbes are in a given setting, they could be any number of things. You want to have an agent that can handle all of those. And likewise, you don't want to have an agent that's going to be specifically devoted to killing just one particular organism when in fact there's many that could occur in a community of organisms in whatever setting you're trying to um, remove microbes from. So you want them to be fairly broad spectrum. And of course, low toxicity. That's referring to its effects on you. So if it's low toxicity for you, that's good. You're not going to be made sick as a consequence of using it. You have to be able to penetrate. So liquids and gaseous chemicals can penetrate porous surfaces like wood and cutting boards, or foam in, say, couch cushions, cloths, things like that. You need sometimes to be able to kill microbes deep within them, and these can achieve that. And hopefully, some of them are non-corrosive and non-staining. You can find things that are that way. Of course, there are some that are not so desirable if they're going to cause corrosion or staining. It just depends on what you're using them for. If they're highly corrosive and they're highly staining, it may mean, not always, but it may mean that you don't want to use it on tissue like mucous membranes and skin. Of course, iodine is sort of an exception to that. It's such an outstanding antiseptic that it's frequently used. Just don't want to dump it all over clothing or anything like that. And generally, too, a lot of these things, especially those that are potent enough to use in a home, they're pretty affordable and they're fairly readily available. It's good news. So yeah, these germicides, these chemicals, which are often called germicides, by the way, are not all created equal. Some of them are a whole lot more intensive in terms of how they kill as opposed to others. So if something is a high level germicide, it more than likely can be utilized for sterilization purposes. So it'll kill everything, including endospores. So if there's some indication that you're working with something that's a high level germicide, that's good to know. These may sometimes be, because of their harshness to microbes, they may actually be harsh to humans. So care must be implemented in utilizing them. So when would you use them? Well, if you can't use heat, you've got delicate instruments like, say, endoscopes or other things that you're going to be using hopefully repeatedly because they're expensive and not easy to replace. You can, as opposed to putting them in an autoclave and risking destroying them with heat, you can use some of these chemicals either in liquid or gaseous form. That'll do it. That'll do the trick. Okay, and you can, in some cases, use them on body surfaces, skin and mucous membranes. And that'll remove a lot of microbes, more than would be the case in using many other approaches. And then, of course, you got intermediate level germicides, which are not sterilants, but they can kill quite a range of things. So they're pretty broad spectrum. So fungal spores, not endospores, but fungal spores can be killed by these typically. The tubercle bacillus, that's just a fancy name for organism that causes tuberculosis. Mycobacterium tuberculosis. That's what that is, the tubercle bacillus. That's important to know. That's a pretty bad customer. So if you can kill that and prevent the likelihood of people being infected with it, then that's always a good thing. And quite a number of viruses, especially the non-envelope viruses, who simply use a protein capsid with fibers or spikes attached for adhesion to host cells. Those are a little bit of a challenge sometimes to kill, and these will take them out. And then the low-level germicides are those that are principally used against vegetative forms of bacteria and fungal cells, never endospores, not even spores and fungi, will succumb to these. A number of viruses, including the envelope viruses, will succumb to the effects of low-level germicide. They can use them on skin, but generally not on mucous membranes. And then as far as the factors that affect the activity of these chemicals, the nature of the material being treated, is it porous or is it dense so that there's no porosity? That's going to affect how readily these work. How contaminated something is, it just how many microbes are there. If you got a whole bunch, it's harder to make these things work, even if they are intense in terms of their effects. The level of contamination could be really extreme, and so would require, appropriate chemicals or longer application of them. The time of exposure, the longer you expose, obviously, the more effective they're going to be. And also the strength of the chemical action of the germicide. I think these are all pretty straightforward things that kind of, are self-explanatory. All right, so here are the different germicidal categories. We're going to go through each of these in turn. So rather than me looking at this and going down this list right now, I'm just going to go from one to the next and talk briefly about their chemical makeup and how these function. So the halogens, all right, so if I had a periodic table up here and I could show you that. As you go to the right in a periodic table, the elements listed become more and more what we call electronegative, okay, which means that, that's horrible, I apologize, but you know what I'm spelling here. Writing with my finger. It's hard. So electronegative. That means that the substance, whatever it is going to have a strong attraction for electrons. So to aid their stability, they take up electrons from other sources. And in the course of doing that, they take on extra negative charges and become negatively charged. So they have this high affinity for electrons. And the things that they get their electrons from are other molecules, and those might just happen to be molecules that make up the cell's structure, the cell wall, the cell membrane, other parts of the cell. These halogens will attack those proteins and other substances there, thus disrupting the function of the cell. So perhaps, one of the most widely used halogens, at least outside of the body, when we're talking about outside of the clinical setting, like in a swimming pool or countertops, that sort of thing, we're going to use chlorine-based disinfectants generally. So chlorine exists in nature as Cl2, and when that goes into solution, the separate chlorine atoms separate and they become chloride ions. Now, sometimes chlorine, when it's part of a molecule and becomes ionized, it's a little more effective in terms of its stealing of electrons. By the way, taking electrons from something else, which is what halogens are good at, that's oxidizing, and that's oxidation. So that's what we're doing with these. And instead of just plain old chloride, which is, oxidizing, this stuff down here, hypochlorite, is an ion that has that formula. It's got a hydrogen, it's got an oxygen, it's got a chlorine, and together those can take up an electron and take on a negative charge, be very oxidative. There are salts of hypochlorites, in particular sodium hypochlorite, which you can put into solution, and they're excellent disinfectants. That's what bleach is. Bleach is sodium hypochlorite. And you may not be aware of this, but your own body actually has the capacity to produce small amounts of bleach. Your neutrophils and some other of your immune defense cells can actually make this and release it into the surroundings, which then is just a generally effective killer of foreign cells that make their way into your body. So when you get really sick and you just feel horrible, part of that is because your own body is releasing hypochlorites for that purpose. But there are chloramines and other substances, all of which have as their basis the chlorine atom. And so because they're so strongly oxidizing, when you place proteins adjacent to them, the proteins are going to be denatured. And in particular, that's going to happen in places where you have amino acids in the proteins that contain sulfur. Cysteine is one of those. So if you've got a piece of DNA, I'll put it down here. Not DNA, this is a protein, let's say. And let's say here's a protein. And in places where you have sulfur residue, sulfur containing amino acid residues, those can join together by way of what are called disulfide linkages. So there's a disulfide linkage or disulfide bond. This little string is a protein, and these S's are sulfur-containing amino acids. And that helps to maintain the shape of the protein. What chlorine-containing disinfectants will do is they'll go in and they will literally disrupt those bonds. And that'll denature this protein, and it'll lose its shape. So that can kill organisms. That can kill microbes. And so in terms of their effectiveness, they are intermediate. All right, so they're not going to take out endospores, but they can take out fungal spores and some of the more resistant types of vegetative bacterial cells. So they're quite effective, and they're cost effective. They're relatively cheap, and not terribly toxic. I mean, they are to some extent. You don't want to go breathing in lots of chlorine fumes because it can damage your tissues. But if applied properly and in the right setting, it can be quite effective. Now, they are unstable in sunlight, so that's why you put bleach in an opaque white container. Or if you had it in a laboratory, you could use an opaque brown bottle. Bleach solutions would last longer in those cases. Of course, they interact really well with organic matter. So if you got blood or fecal material or anything like that, and you're, pouring some chlorine bleach on it, ultimately the bleach is going to oxidize the organic matter, and that once the chlorine has taken up electrons, it's no longer effective. So the dirtier something is, the more of this you're going to have to apply. So you can see here the different uses. Small amounts of chlorine gas can be bubbled through water or small amounts of bleach, for example, can be mixed with water, and it's still potable, it's still drinkable. and it will kill a lot of the organisms in it so that you don't get sick. It may not taste all that good, but it's not going to be um, potentially a source of pathogens. In sewage treatment and wastewater treatment, and um, disinfecting inanimate surfaces, yeah, chlorine-based products work well. A better choice in a lot of instances, especially if we're working in a clinical setting, so as far as antisepsis is concerned, iodine-based antiseptics and disinfectants are highly sought after and very useful. Iodine is over there to the right-hand side of the periodic table as well, and iodine atoms are very electronegative. And they'll do much the same as chlorine, but not quite to the same extent, which has the advantage of making it more useful on body surfaces. So oftentimes iodine is complexed with an organic molecule, which acts as a sort of carrier for it. And we call those iodophores. And betadine is an important product used in the clinical setting, which is made using iodophores. And these two will interfere with disulfide linkages in proteins and can cause disruption of the proteins as much the same way as chlorine, but in a gentler, less harsh way. And so we can use betadine to clean an area where we're going to do a hypodermic injection, or we're going to do some incision with a scalpel. You can clean, sutured wounds and other injuries, and just really, really effective stuff, and helps to prevent infection and sepsis and all of that. It can be delivered in a lot of different ways. So, which of the following is not true about hypochlorites? I didn't look at this ahead of time. So, yeah, it's letter D. It slows the release of iodine. That's just, if you read all these, that's the one that is goofy and doesn't make sense. But, yeah, it denatures, and it's light sensitive, and you can use them to disinfect water, right? So there's that. So then another class of chemicals that can be used for disinfection, antisepsis, and so forth are the phenolics. And so these are all based on addition of functional groups to this molecule right here. This is the original one of the phenolics, and that is phenol, which is sometimes called carbolic acid. So that's the old-timey name for it. It's actually two separate words. I apologize. I strung them together in one string. But yeah, carbolic acid. Remember, this was made famous by Joseph Lister in his surgical practice in the 19th century. He was using it. He soaked his sutures in it. He cleaned wound sites, incision sites, and so on. They even washed their hands with it. There's a lot of hand washing. He was a big champion of that, and widely used. And you can see its structure. This is basically a kind of a symbol for it. This little hexagon that has a double ring, a double bond, followed by a single bond, by a double bond. They alternate all the way around. That's referred to as a basic aromatic ring-shaped compound. And what we've got in here, each of those corners is a carbon atom. So it's implied. They don't actually show the carbons, but they're in there. So there's 6 carbons, and hanging off of each one of those is actually a hydrogen atom. They don't show those either. But here, instead of a hydrogen atom, there's an OH group, a hydroxyl group. Okay? So it's essentially an alcohol. An aromatic alcohol, I guess, is how you would classify it. And it does have a very characteristic odor. If you've ever smelled chloroseptic throat spray, or if you've ever used carbofucin, as you have, in the laboratory when you do acid fast staining, you know that smell. Okay, so this is a very potent germicidal substance, and it'll kill bacteria, fungi, viruses, but only vegetative forms of those. Endospores are not affected by it. And it's been used a long time. In fact, at one time it was the gold standard for measuring the effectiveness of other chemical substances. They used to compute what's called a phenol coefficient. So that's a measure of the effectiveness of a chemical in comparison to phenol. So if you had chemical X and you had phenol and you used them both to try to kill microbes and you discovered that they were about the same in their effectiveness, the ratio of their effectivenesses would be 1. So if you had another substance and you said its phenol coefficient is 1, that means it's exactly like phenol, and if that's good enough for you, then you can go for it. If it had a value higher than 1, that would mean that it was more effective than phenol. And if it was smaller than 1, then it'd be less effective than phenol. So that's how highly thought of phenol was. This is a substance that can work in multiple ways. Because it's got just a little bit of oxygen in it, it tends not to be strongly charged or polar. And so it's kind of hydrophobic. It's kind of nonpolar, which means it'll pass through lipid-containing cell walls like the outer membrane of a gram-negative, or through the cell membranes, which have lots of phospholipids. So they're disruptive of those things. And then once they enter the cell, they can precipitate proteins, which basically is the same as causing coagulation. So phenol can do all of those things. Now, because it was used very widely, organisms began to evolve resistance to it. So other kinds of phenolics have been developed, and if you look at different disinfectant chemicals that are commercially available, sometimes you'll see these names listed, like cresols, chlorophene, which here you can see combines a halogen. You got some chlorine in there, so you can combine the effects of halogens and phenolics and get maybe a synergistic effect of those. And then this is hexachlorophene, which you can see has a lot of chlorine in it. And plus it's got 2 phenol moieties in there as well. So Lysol, which, will kill coronaviruses. That's on the side of the can. It can disrupt, envelope viruses and bacteria and so on. And then triclosan is something that's very common in the clinical setting. We see it in antibacterial soaps and so on. That too is based on a phenol as baseline or germicidal agent. And then we have chlorhexidine. So hexane here refers to a 6-membered ring. These are, it's similar to phenols. We got some halogen in here. We got some chlorine in there. So some of the trade names for chlorhexidine are Hibiclens, Hibitane. Those are things too, again, that are commonly used in clinical settings. Some of you probably use them and know way more about them than I do. But you can see that they are surfactants. That means they disrupt cell membranes. It's just a fancy way of saying that. And they're also protein denaturants. All right. There's that. And then we have alcohols as well. Those can be important antiseptics, and occasionally are used in a disinfectant capacity, but more often than not, they're going to be used as antiseptics. And so we've got different kinds of alcohols. The 2 main ones are ethyl and isopropyl alcohol. There's also methanol, which is known as wood alcohol by some. Methanol is very toxic, and it can be used as an agent to denature. We talk about denaturation of alcohols. If you denature an alcohol, basically what you're doing is altering its chemical properties so it can't be drunk. So denatured ethanol would have a little bit of wood alcohol and a little bit of methanol in it, and that's dangerous. I should put a skull and crossbones on that, because if somebody were, you know, intrigued enough to try to drink that, they would probably wind up hospitalized and probably dead. But ethanol and isopropyl are useful in the clinical setting, especially isopropyl. Ethanol, this is ethanol. It's also called ethyl alcohol. Ethanol is commonly used in museum settings as a preservative. So you can preserve live, or tissue, what was once living tissue. Fish or snakes or even plant parts can be preserved in ethanol and placed on a shelf in a museum, and so you can come back to that and look at it decades after it was first collected. So it's a preservative in that sense. Isopropyl, you can use this for when we do venipuncture. You can swab or prep, say, the cubital region of the arm, and draw blood or do an injection or whatever you're going to do using isopropyl. Now notice that the concentrations of isopropyl range from 50 to 90%. That's when they're most effective. And by the way, this means what we're doing is we're taking a certain amount of pure isopropyl and adding it to 100 milliliters of water. So you have 50 mils of pure isopropyl, and it goes into 100 mLs of water. You've made a 50% solution. Percent means per 100. Right? If you took 70 mils of pure ethanol and placed it into 100 mLs of water, you'd have a 70% solution, and so on. So it turns out that alcohols are better when they're not completely concentrated, when they're not pure ethanol or isopropyl. They work better when they're watered down a little bit. They function better as surfactants in that way. So that's interesting. So they are often surfactants, and that's the reason for that is related to the reason why phenolics are good at disrupting cell membranes as well. They have very little oxygen in them. So here's ethanol's chemical formula. It's got two hydrogens, or two carbons. It's got 5 hydrogens, and then it's got an OH group on it. Okay, so it's mostly carbon and hydrogen. Isopropyl is C3. It would be H8, and it's got an OH. I think that's right. No, it's H7. Yeah, it's H7. Sorry. Anyway, you can see, again, carbon and hydrogen. What this means is these are not, they don't contain elements that become highly charged, and so they are principally hydrophobic. Another word for that is nonpolar. So they like to interact with other things that are hydrophobic and nonpolar. It turns out that cell membranes are like that, okay? So they like each other, and they more or less mix together. That disrupts the membrane. All right. And then they coagulate proteins. Proteins that were in solution come out of solution, they clot. in the presence of alcohol. They'll do that. Actually, they'll do that to nucleic acids too. They'll cause them to clot. All right, so there's that. Alcohols, outstanding surfactants. You know what that means is they combine with lipid-containing membranes and break them up. Now, another substance that doesn't fall into any of those categories that I've previously gone through is this stuff, H2O2. It's hydrogen peroxide, okay? So when this goes into solution, these oxygens in the hydrogen peroxide are extremely electronegative. So this is a very, very powerful oxidizing agent. And so it can be destructive. And just as a side note, oxygen generally is kind of toxic anyway. So just plain old oxygen gas, for example, in the air we're breathing in, it comprises about 20% of that atmosphere. If it was to be any higher than that, let's say we elevated the oxygen concentration to near 100%, you'd think, gosh, that's great. That's going to be, that's going to really energize us if we were to breathe that kind of oxygen. And it's true, you probably would experience some good effects of that, but it's also quite destructive, and you can damage tissue. Oxygen is what causes metal to rust. It's what causes plastic to become broken down. It's what causes wood to weather and so on. So it's hard on organic substances in particular. So H2O2 is even more destructive. H2O2 and other oxygen-containing substances that are pretty damaging to cells are known as free radicals. And they're often produced as a byproduct of metabolism. So you actually produce some hydrogen peroxide with the oxygen that you're taking in. It just sort of spontaneously forms. And then there are, hydroxide ions, OH minuses, and superoxides, and, things like that are really destructive. So you have to have mechanisms in place to detoxify those things to keep you alive. And we do. We've got, in our bodies, we've got catalase, and I know I've talked about this before. That's an enzyme very abundant in all of our tissues, especially our liver, and it'll break down H2O2. Many organisms don't have that. And often these are pathogens, especially anaerobic forms. So if we want to kill those, we can use H2O2. And even if something does have catalase, we can overwhelm it with hydrogen peroxide, especially in gaseous form. We can turn it into a vapor, and we can waft it over surfaces we want to disinfect, and we can approach sterilization. We can actually use it as a sterilant. So it's really outstanding stuff. It's used as an antiseptic. It's used as a sterilant in some instances in a clinical setting. But yeah, you can see it. Here's another word. Another word for you to know. This is sporicidal. It means it kills spores. So anything that will kill endospores is sporicidal, and it's the very definition of a sterilant. So this device down here is one in which you can place things like endoscopes or other equipment you would use in a biomedical setting. Maybe in a dentist office, you've got things that you're wanting to sterilize effectively. This device here will flood this chamber inside, wherein you've placed your object with hydrogen peroxide gas. And if that's present for long enough, you will sterilize it. So there's a good one there. And then we have the aldehydes. Okay, so again, going back to hydrogen peroxide, it's an oxidizing substance. It oxidizes and is destructive to chemicals generally. But then we've got the aldehydes, and the aldehydes have a chemical structure. So they're going to have a carbon and hydrogen and maybe oxygen containing section that's got all kinds of carbons and hydrogens bound. But the key, the thing that makes it an aldehyde, this is the signature of an aldehyde, is it's got a carbon, and then it's got an oxygen with two bonds between the carbon and an oxygen, so double covalent bond. And then over here we simply have an H. So if you take that out, it's this, that little deal right there. That's the signature of an aldehyde, right? And so down here it shows the forms of different aldehydes. You see formaldehyde. Then we've got our signature aldehyde, group, and attached to that is a single hydrogen. And then acetaldehyde. There's our aldehyde group. Attached to that is a methyl. And then we got, here's our aldehyde here. And that's got an ethyl group, right? And so on and so forth. You can see all of these different kinds of aldehydes. Even these down here, aldehydes. Now this down here is not an aldehyde. That's a ketone there, acetone. The others are aldehydes. I don't even know why that's in there. But anyway, so these aldehydes, how they work is this part of them here, that part is taken from the aldehyde which contains them, so acetaldehyde, formaldehyde, whatever it is. And in the presence of organic molecules, this thing here will be attached to that molecule. So if it's a protein, it'll receive this. That'll get tagged onto it, and that'll ruin that protein. If it's a nucleic acid, again, it'll tag it with that. So that's called alkylation. Anytime you take an organic functional group, like this aldehyde group, and you take it from one molecule and put it onto another one, you've alkylated it. Okay? So alkylation of proteins, that disrupts their shape. They're no longer functional. That will denature them. That'll kill them. And of course, alkylating DNA will likewise do the same. It'll disrupt its functionality. So now, in a clinical setting, there are two aldehydes which are commonly used. One of them is fairly safe and very effective as a sterilant, and it's one that's more frequently used these days, and that's called glutaraldehyde. And I think that's spelled right, G-L-U-T-A. It could be G-L-U-T-E. But anyway, that's glutaraldehyde. And notice it's something that we can use small amounts of. Just 2 mLs of that in 100 mLs of water gives us a 2% solution. And that is a really potent sterilant. So you can clean up labware, instruments and so on using that. So that's a high-level germicidal agent. Formaldehyde is one that was used a lot formerly. Of course, now it's still used in the mortuary business, in preparing, embalming deceased folks. And so formaldehyde is a component of embalming fluid. But it's used for tissue preservation. Say a pathologist would use this to take some tissue that's suspected to be cancerous, and they might fix it in formaldehyde and prepare it for viewing under the microscope to preserve it. So, but yeah, it can be used as a preservative. Preserved wood, treated lumber. There's a certain amount of formaldehyde used in that. It's used in a lot of other contexts. It has been for a while, but it's been, for say 4 or 5 decades now, common knowledge that it is a carcinogen. So formaldehyde is a carcinogen and will cause cancers. There's no doubt that it will do that. So, and it's pretty toxic and it's pretty noxious. It burns mucous membranes. So its use has been limited as a result of that. And so one form of formaldehyde that's commonly used is a water-based solution known as formalin. So you can take the formaldehyde and put it into water, um, make this 37% aqueous solution, and that's formalin. Anyway, that's used, like I mentioned earlier, with alcohol in a museum setting. Formalin's often used in museums to fix tissue, biological tissue of fish and other specimens so that you can have them long term and use them um, as vouchers to say, well, this fish occurred in this stream at this point in time, and so on and so forth. So it's got that utilization too. Then among other chemicals, so those are mostly liquids. Among other chemicals, we've got gases and aerosols, right? And so these are placed in a mist or a vapor, and are used as disinfectants, and sometimes can approach sterilization levels of disinfection. So two of them, ETO, ethylene oxide, and then of course propylene oxide is often abbreviated as PO. Those are important gases that are used in um, reducing microbe loads in a lot of different things. And like glutaraldehyde, formaldehyde, these are strong alkylating agents. And especially with ETO, you can apply that. It's applied under pressure in much the same way as one would use moist heat in an autoclave. You can take these chemicals and in a pressurized chamber like this, which is sometimes called a chemiclave, right? You can apply your ETO. And the pressure actually causes it to be driven into porous surfaces, and it will alkylate. It'll add organic side groups to proteins and nucleic acids, thereby rendering them useless. So it's an alkylating agent, and it can sterilize. So if you've got plastic items like toys and so on, and you're marketing those, and say something a little kid can put in their mouth, uh, you'd want to reduce the microbe load of that plastic object prior to selling it. And this is one way to go. You can disinfect this way. The good thing about these gases is that they're not residual. You apply them and then they go away. So kind of like when we irradiate things, you apply it and it goes away. So you can disinfect plastics. You can package something in, say, paper or something like that, and this gas can go through that and disinfect whatever's in there, and it's going to keep it free of contamination. And even foods, dry foods like nuts and cereals, you can reduce the microbe load in those using. All right, so some other chemicals. We've got detergents and soaps. Well, these frequently act as surfactants. One component of a lot of soaps are what we call quats, quaternary ammonium compounds. No, ammonium is a nitrogen, and bound to it are 4 hydrogens, and it'll take on a positive charge. So these are all based on an ammonium molecule. But instead of 4 hydrogens being attached to the nitrogen, being substituted onto the nitrogen, we have other substances. So these R's here in this general symbol for a quaternary ammonium compound, these R's represent just general organic things that could be attached there. So the sky's the limit. I mean, you can stick, say, a methyl group in here, CH3, and put an ethyl group here. something like that. And on and on. You've got a lot of different variants. Heck, you could even probably stick halogens on there and produce a variety of substances. So there's a bunch of different ones of these quats, and they're, like I said, commonly added to a soap. A soap is a substance that, when mixed with water, will create suds. It'll bubble up. And unless there's been another substance added to it that is a disinfectant or an antiseptic, it won't have a killing effect. Now, it will help with degermation. So if you're scrubbing some skin that's dirty and you suspect that there might be microbes on there, and you're using a soap, the soap will help to lift the dirt so it can be washed away. That's a mechanical means by which you can reduce microbe loads. But if you stuck a quat in there, the quat could act as a surfactant, and that will kill microbes as well as just make them go somewhere else. So that's how antibacterial soaps work. Both of those things. Suds up, they lift dirt away, they lift organisms away, and they penetrate organisms and kill them. So now the quaternary ammonium compounds have been widely used, and I guess the verdict on them is that they have a very low effectiveness in many cases. I think a lot of organisms have adapted to them, in much the same way as antibiotic resistance has arisen. So yeah, this compares soaps without germicides versus those that have, say, a quat in them. And this is applying them to different cultures, I guess, of bacteria. And so if you take a culture of some bacterium and introduce a germicidal soap into it, you can see that over time the number of cells will decline. Maybe not to the point where they go away entirely, but the number is lower. And a lot of times, whether or not you develop an infection is going to be related to the number of cells that are present that could infect you. So germicidal soaps, you can see, are effective. But look at the time course of this. All right, so they've got to be applied fairly rigorously, and they're not going to sterilize anything for sure, but they can actually help you to achieve antisepsis or say disinfection if you. And then you can see with non-germicidal soaps, their effectiveness is essentially zero as far as killing microbes. Now, notice how this is a kind of a line of fit to this jagged curve here. That's sort of the average condition. And notice that says there's no slope at all. Here, slope. And so there's neither decline or increase. So what have we achieved? Well, we've kept the population of bacteria static. And so at best, what we can say about non-germicidal soaps is that they are microbistatic. Right? This is actually germicidal or microbicidal germicidal soap. So anyway, there's that. Okay, so with regard to these chemicals, which of the following kills by producing oxygen radicals? And of the things that are up here, the best one of the choices would be hydrogen peroxide. That's an oxidizing substance and the way it works. Now, some miscellaneous chemicals. I mentioned this way back. There's that little diagram that showed a protein and how you can heat it a little or a lot, or and get different results. Or you can add a heavy metal and get this oligodynamic action or effect, and that results from metal atoms literally attaching to the active sites of the enzymes. Right? It blocks those, and so substrates can't get in there. And so metals, sometimes by themselves, sometimes in compounds containing them, things like silver and mercury, those are heavy metals that can produce this oligodynamic effect. And they inactivate proteins. They don't denature them, but they block the active site. So it's a form of, I guess, inhibition. It's actually technically known as non-competitive inhibition. Ultimately, if you were to apply the heavy metal and it didn't kill everything, and you didn't apply any more heavy metals after that, organisms tend to be able to overcome them after a while. But they can be effective sometimes. And this is a petri dish over here, and it shows bacteria growing all over. This is bacteria, but you can see here's a clear spot and here's a clear spot here. And in the center of those zones of inhibition, you have different examples of heavy metals. So the silver amalgam is the stuff that they used to fill teeth with. So if you had a dental carie or cavity and they plug that with some filling, that's it, right? And that's part of the reason those were effective. It prevented further decay of that hole in your tooth. And gold also is used as a filling material. And you can see here that it's having that effect as well. It's killing organisms and creating a zone of inhibition around. So these are not super highly effective, and their utility is kind of limited, so you don't see them that much anymore. Used to be, if you got a scraped knee or something like that, folks back in the 20th century, especially in the mid and earlier parts of that century, would apply what's called bartholate, which is a tincture of a mercury-containing salt. So tinctures are made with alcohols. So if you were to solubilize some of that mercury-containing salt, which gives a reddish color in alcohol, you produce merthiolate. You can sort of daub that onto a wound, and it'll help to, prevent infection. Although I've seen, I believe, studies where they've applied that and they found that it didn't really have much of an effect. Maybe it was microbistatic at best. But yeah, you can see all those different heavy metals, and they account for this oligodynamic effect, which is a low-level germicide effect. And dyes can be used. So dyes enter cell walls, cell membranes, and they lodge there, and so they disrupt the ability of those barriers to prevent things from crossing. So if an organism needs some sustenance from some item in its surroundings, the dye is present in its outer covering, in its cell wall and cell membrane, may not be able to get the nutrition that it needs. So they can be effective antimicrobial agents for the very fact that they attach to cells. And so a lot of the what we call aniline dyes, which would include things I think like crystal violet, can be effective, especially against gram-positive bacteria and some fungi. And they've been used for antisepsis and wound treatment. But they have a pretty narrow spectrum of activity and a pretty low level in their effectiveness. And then we've got things that are not necessarily destructive, not killing, but more microbistatic, and that would be mainly acids and alkalis. So using acids like vinegar, which is acetic acid, or the acid in lemon juice or lime juice, citric acid, and others. That's something that's been done for millennia, essentially. And likewise, you can use alkaline substances, so bases can be utilized. Lye, for example, is essentially sodium hydroxide, NaOH, and you can get that by taking hardwood ash. So if you burn oak and hickory and stuff, take the ash, and then mix that with water, and then pour off the solution that you get, you'll have sodium hydroxide in that. And, that's fairly potent stuff, and it will disrupt the activity of microbes. It's a very strong oxidizing agent, whereas acids are reducing. Acids actually add electrons to things. So anyway, whether we're using vinegar or we're using sodium hydroxide or lye, as it's called, lye water, we can disrupt bacterial and fungal activity. And you can see like this propionic acid. If you've ever read, say, the ingredient list on a loaf of Wonder Bread, look there sometime, and you'll see listed things like propionates and other eights, things with ATE on the end. Those are frequently going to be organic acids that are present there, used as preservatives. Lactic acid, that's what's in yogurt and gives it sort of its tart taste. And that's going to prevent overgrowth of organisms. We use, we don't use it, but when we make sauerkraut and other fermented forms of cabbage and other things like that, kimchi, organisms of fermentation will create lactic acid, and that serves as a preservative. And benzoates and sorbates, those inhibit fungi like yeast. So these are all mainly, when we use them industrially to control microbes, we're using them as microbistatic agents. They're microbistatic meaning. Acetic acid, you should know that's vinegar. So on and so forth. So there's that. All right, so I'm done with that lecture. I've got one more to do. Well, I'll break it up in multiple parts, but one more chapter, and that is chapter 12, and it's over the chemical agents principally that are used to deal with infections. So, say your disinfection and your antisepsis and degermation, these other things haven't worked, and you've now got an infection. What do you do then? So we're going to talk about chemotherapies, drugs that are used to destroy infectious agents in our body. So that's coming. I'll get these up, and like I said, we'll have an exam shortly over this stuff.